everyone, and welcome back to Physics 4A. Today we'll be talking about fixed axis rotation, and I do have my video on just for this video because we will be talking about the right hand rule, and to do that I need to show you what I do with my hands so that you can understand it. Okay, so let's go ahead and get started with some rotational variables. So the first one is going to be our angular position of a particle, okay? And so this will help describe where that particle is in space. And so that would be this angle here. Then we have the arc length S, which is going to be the length that particle will sweep out along its motion. And then we have r, which is our radial vector, so that'll be the radius at which that particle is. Okay, and so we can relate all of these through this equation here. We have theta equals s over r, okay, and that is through some trigonometry. And then we also have s bar is equal to theta bar cross r bar. Okay, so this shows us that they are perpendicular to each other. Okay, so I can go ahead and show you the right hand rule here. I'm not sure that I showed you it in the past. I cannot remember, but let me show you this or give you a refresher real quick. So when you're looking at a cross product, we can figure out what direction our resultant will be in, or that S bar here. Just by using our right hand rule. Okay, so our right hand rule, we start with this first vector, and in my case it's pointing up. Okay, so I'm going to go ahead and put my hand in that direction of motion, so it's going to be pointing up. Okay, then it crosses to R, so then I will curl my hand, and this is my right hand, towards the direction of the R bar. And so it's kind of in between X and Y coming at us. So I'm going to go ahead and make my hand go right here and then cross this way. And then whatever way your thumb is pointing is going to be your result. Okay, so my S bar is then in this direction. Okay, so it's a little bit tricky. It takes some time to get used to. I'll go over it a few more times throughout this lecture so that we can understand it. Okay. All right, then we have our angular velocity, and that is going to be the time rate of change of the angle theta as the particle moves in this circular path. So we have it here, theta, and so it's going to be the time rate of change of that change of angle, okay? And we have our instantaneous angular velocity down here. And we can take the limit of the average angular velocity, omega bar. Okay, that's what the bar means. It means average. And so that would be the change in theta over the change in time. So the change in this angle theta over the change in time. Okay, and so then our instantaneous angular velocity, omega, will be equal to d theta dt. Okay, note the similarity between that and velocity equals dx dt. Okay, so theta describes a position, just like x does. Okay, so moving on from there, we'll talk more about angular velocity. Sometimes we want to relate that to tangential velocity. Okay. Tangential velocity is going to be the velocity that is tangent to the radial vector, okay, or orthogonal. Okay. Say we have, this is going to be an example real quick, say we have two particles that are rotating on the disk here, and they have different tangential speed, and that is because it depends on the distance to the axis of rotation. Now, let me go ahead and put that into an example. Okay, so say you're on a merry-go-round. I know we're not kids anymore, but we could watch people on a merry-go-round, maybe, or watch kids. Okay, so, but you know what I'm talking about, okay? So we're on a merry-go-round, and you're on the outer horse, okay? And somebody else is on the inner horse, say your friend or cousin or whoever it may be, okay? And you guys are traveling, okay? You will be moving faster, it seems like, okay, than the person on the inside, okay? So you're on the outside one and they're on the inside one, and you seem like you're moving faster, okay? That's because your tangential speed is faster, but your angular speed or your angular velocity is the same as the other person, okay? You're sweeping out the same angle as they are as a rate of time, but tangentially, you're having to move faster. I think of it as like you're having to make up more ground than the other person. So this particle on the outside, they're having to travel more, right? The distance is larger because they're at a greater radius from the center of rotation, okay? Or the axis of rotation, okay? Hopefully that makes sense. Okay, let me erase that real quick. All right. So, we can relate our velocity with the angular velocity and our radius, okay? So if we have an angular velocity vector that is along the z-axis here, okay, then we will have counterclockwise rotation. So if we have a positive, we can say positive angular positive angular velocity, or I could say positive omega, then we'll have the counterclockwise rotation. Okay, so then, and this is by the right-hand rule. Okay, it's flipped for you guys, but hopefully you see that this is someone's right hand. Okay. All right, so then if I have a negative angular velocity, it's pointed down, then I will have, let's see, this way is going that way, going this way, that's counterclockwise. I wanted to make sure. Then we'll have clockwise rotation. I know logically it makes sense that it would be opposite, but I wanted to be sure. Okay. So then, this is just kind of getting you in the groove of that same thing that I was just talking about. So if I have, excuse you, my dog's growling at me. She's been a little needy. She just had a little surgery. Nothing big, but just a little procedure. What? You're very needy. Okay. Anyway, so this is just showing you these different relations if we have a positive omega or a negative omega. And when I say positive or negative, I mean along the z-axis, okay? So if we have a positive omega, so we have that it's this way, okay? We go omega cross r, and then cross r, then we point towards our velocity v. We have omega cross r, we have our velocity v. Okay, we would also do it in a different way. So I would say, we can also say omega, so pointing your hand in the positive z direction, and then curling your fingers towards r. Okay, so curling your fingers towards r, and then v will be in the direction of your thumb. Okay, this can be kind of uncomfortable if you do it for too much. And then you can do the same thing. Okay, so we did this way. Now if we did this way, and then curl our fingers towards R, and now V is pointed in the other direction. Okay, it takes some practice to get used to the right-hand rule, but once you get the hang of it, it's kind of simple. It's not ever like super easy, but it just takes your brain some getting used to, okay? All right, so let's go ahead and do an example here. This is example 10.1. It states a flywheel rotates such that it sweeps out an angle at this rate. So here's an equation here, radians. The wheel rotates counterclockwise when viewed in the plane of the page. Okay, what is the angular velocity of the flywheel? Okay, so this is some rate that it sweeps out. We want to find the angular velocity. Okay, well, it was pretty much given to us, right? So angular velocity is omega. From this equation, we have that omega is equal to 45 radians per second. Okay, that one was pretty basic. It was pretty much given to us. Okay, now we want to know what is the direction of the angular velocity. Okay, so the wheel rotates counterclockwise when viewed out of the page. So we're going to pretend that the computer screen is our page. Okay, and so that's the plane. It rotates counterclockwise. So if it's rotating counterclockwise on our plane, okay, so clock here, counterclockwise would be going in this direction. Okay, so this is counterclockwise. Put that there. So we want to know what the direction of the angular velocity is. Okay, so what we'll do is we'll use the right-hand rule to figure out the direction of the angular velocity. So we said that our rotation here is counterclockwise, okay? And so what we'll do is we'll take our right hand, again, this is my right hand, which is kind of confusing for you guys, and we're going to go ahead and curl it in the motion or the direction of motion of the wheel. So in my point of view, I am turning it in the counterclockwise direction. Okay. So I'm going to go ahead and do that. And then the thumb, my thumb, is pointing towards me. Okay. So that tells me that the direction of angular velocity is towards me, or we would say out of the page. Okay. So the plane of the page. So this would be out of the page. Okay. All right. Then we want to know how many radians does the flywheel rotate through 30 seconds. Okay. So we have time is equal to 30 seconds. We have theta is equal to this equation here, omega t. Okay. Yeah, so we can just go ahead and plug in our form here, or our formula. We have 45 radians per second, and that'll be times our time t, which is 30 seconds. And so if we plug that into our calculator, we get 1,350 radians. Okay, I won't be able to go on to the next part in this video, but I will continue this in the next one, and then we'll go ahead and continue our lecture as well.